Hello, everyone. We are going to look at conservation of momentum some more, like we did in video 3, but we are going to specifically be looking at collisions. Uh, there's a whole set of types of problems that you'll see in physics where objects collide with each other, something happens after the collision, and then we use conservation of momentum to look at that. So a collision is usually just going to be two objects. We don't generally see collisions with three or four objects at once. It just would get a little bit complicated. So a collision, we'll draw out the example of this or an image of this, but we'd have two objects with at least one of them moving before the collision. And that's what we're going to see for our types of collisions. And there are uh, three possible types. We're going to categorize these collisions by three types where we're going to look a little differently at um, the equations we use for those. Two of them are actually the same equation, but we'll talk about some other differences between the three types. All right, to understand what these three are, we're going to go through one by one and observe. So I'm going to draw a little image over to the right of like a surface, and then you've got your two objects. Now they could both be moving. That's often the case. They don't have to be. You'd have mass one, mass two. And let's just have them, sure, let's have them both be going towards each other. Generally, they're going to be going towards each other. You could have both of them going to the right, but M1 is going a lot faster and it catches up and collides with M2. You could also have one of them be stationary. So M2 could be not moving at all. Really, anything that allows them to collide will work for the setup or what's happening before the collision. But we'll just say that they're going head on towards each other. And you can look at there's some things like based on how much bigger or smaller one mass is than the other. If one of the masses is larger than the other, or how much faster one is going than the other before they collide, all those things could affect what type of collision it ends up being. But the first type of collision that we're going to look at is elastic collision. We're going to talk about two ways to identify what type of collision it is. One is generally what happens after the collision. So what we generally see here is the objects bounce off each other. Opposite to their original direction of motion. And we'll quickly visualize or draw what that would look like with red on the right here. So we've got after the collision, we would have like M1 and M2 both going off in the opposite direction to where they were originally going. So now M1 is going off to the left and M2 is moving to the right. So the general visual result of an elastic collision is that they bounce off in the opposite direction. But even though AP is good with this, AP doesn't generally get too tricky and say, oh, we tricked you because it looks like an elastic collision, but it's not, despite the fact that they don't get too mean with that. The way to actually tell whether a collision is elastic or not is something else, and that is elastic collisions are really defined by kinetic energy being conserved. Now, we're going to talk about conservation of momentum in just a second, but I'm misspelling my word here. Conserved. But going back to energy, both objects were moving, and it could have been that one was moving, but the other one wasn't. That's very possible. For elastic collisions, generally, they will both be moving. But if M1 and M2 both were moving with some amount of velocity, that means they each have kinetic energy. So you could find out what's the kinetic energy of object 1 and what's the kinetic energy of object 2. And all of that kinetic energy you have before the collision will be the exact same amount of total kinetic energy after the collision. That's what elastic collision is. So if you run the numbers on, well, I had 5 joules and 10 joules for kinetic energy, so 15 total joules, then you better have 15 total joules afterwards if it's going to be an elastic collision. So that's one way to check it, and the way to know that it's elastic is kinetic energy is conserved. Now, momentum is conserved in all collision types. So all of these collisions. And what we're assuming for that, what allows us to say momentum in all collisions is conserved, is that there is no external impulse. This is what we looked at in our last video, acting on our system. Because when we have a system of two objects like this, and there's some momentum for one object and momentum for the other as well, there's kinetic energy for object 1 and for object 2, we can check things like, is kinetic energy conserved? Is momentum conserved? Back in Unit 3, we would say, well, is there work being done by external forces? That can determine whether kinetic energy is conserved. Is there any thermal energy as the result of friction and drag, or even just the collision itself, which is interesting for elastic? It means that these collisions would really have no sound associated with them because sound and heat are thermal energy. And if kinetic energy is conserved, that means all of the kinetic energy going in before the collision, all of it stays as kinetic energy after the collision, and none of it goes into thermal energy. None of it goes into heat and sound. So these types of collisions, they don't really exist as we collide things on Earth because we pretty much always have a little bit of heat and sound involved. So the things we would call elastic collisions are probably not completely fully elastic, but that's fine. We can live in our physics world where collisions cause no sound. But back to momentum. Momentum is conserved because there are no forces from outside of the system that are acting on these objects in the system. Sure, they collide and put a force on each other. During the collision, M1 pushes on M2. By Newton's third law of motion, we could say M2 pushes right back on M1 with an equal amount of force in the opposite direction. But all of that is internal. The blocks pushing on each other are forces and impulses from inside the system. So with no external impulse from the equation for conservation that we had last video, where we looked at initial momentum equaling final and then accounting for is there any external impulse, now we can just say the starting momentum before the collision, and we'll say the total momentum before the collision equals the final momentum total after the collision. So how do we write that? Well, what that ends up looking like is the following. We're going to take the momentum of both objects before they collide. So we'll say m1 v1, and we'll add in that velocity v1 as how fast the first object moves before it collides. I should have added this before. v1 and v2 would be the starting velocities of both objects. So the mass m2 has its own momentum, mass times velocity, m2 v2. So m1 times v1 is the momentum of object 1 before they collide. m2 v2 is the momentum, mass times velocity, of object 2 before they collide. So putting those together, and as we see here, one would be positive, one would be negative, and we could figure out what the total momentum is. But if we had those two momentum values and we added them together, that'd be the total momentum before the collision. All of that is equal to the momentum afterwards. Now I'm going to label just v3 and v4 as the two separate final velocities of the two objects after the collision. So v3 and v4 here are how fast they're moving after they collide. So the post-collision momentum would be mass 1 times its new velocity v3 plus m2 times its final velocity v4. All right. And that is what conservation of momentum equation looks like for an elastic collision. And we could just note, right, that V1 was positive. If we said that right was positive, V1 is positive, V2 is negative, the starting velocities, and then they switch afterwards. V3 is now positive velocity for object 1, V4 would be a negative velocity. Or sorry, I switched it up. V3 is now negative for object 1, V4 would now be positive or to the right for object 2 after they collide. Okay, so that's one of our types of collisions, the elastic collision. We've also got inelastic collision. And for this one, as with the elastic, there's sort of a way to visually clue you in that it looks like it's going to be an inelastic collision, and that would be both objects move at different velocities, but in the same direction after the collision. And the other way to check for this one is it's also, and this is really the one of the better ways to check if you wanted to confirm. Thankfully, again, AP doesn't really make you do this too much. It's not like every single problem they're going to make you go in and check your kinetic energy. But technically, this is defined by kinetic energy not being conserved. In fact, some kinetic energy is being lost to thermal energy, E thermal. I guess I'll just write out thermal energy. I don't need to write the variable for it. So it ends up as heat and sound. Okay, let's draw a little visual for this, what it looks like after they collide. So M1 hits M2. Now, we talked a bit before about it depends on what the masses are. Like, if one of the masses is way bigger, let's say M1 is 4 times as big as M2, or maybe M1 is just going really fast and has a ton of velocity and a lot of momentum before the collision. Either one of those things could result in, if M1 has overwhelmingly more mass or more velocity, basically if M1 has just a really big momentum, then what can happen is M1 and M2 both end up going in the same direction after they collide. So M1 has a velocity, M2 has a velocity, both to the right, and that would be the post-collision velocities V3 and V4. So there's V3 and V4 if it's an inelastic collision. Okay, so they both move together, or both move at different velocities, but not together. So they're not like, we'll talk about that in the next type of collision. But they've got their own separate, different velocities, but they're both moving in the same direction after they collide. And some kinetic energy is lost. If you do the math on this one, and you figure out how much kinetic energy there was before the collision versus afterwards, you'll find that some of it is lost to thermal energy because of the collision itself. When they hit each other, some of that heat and sound gets produced. All right, so the conservation of momentum equation looks like this. In fact, the conservation of momentum equation is exactly the same as it was before. So it's m1 v1 plus m2 v2 equals m1 v3 plus m2 v4. Remember that for each one of these terms, we're just taking mass times velocity because that's how we get momentum. So mass times velocity for the first object before the collision, second object before the collision, all of that starting momentum total equals the ending momentum total for the first object and for the second. Okay. Um, one other thing we could note here is that these velocities are either both positive or both negative. Okay, cool. I think that's it for inelastic. Again, it's mainly just you look at the collision, see what happens afterwards. If you note that they're both going in the same direction, that's pretty much confirming that it's an inelastic collision. You don't have to. There are ways to check if kinetic energy is conserved, but those take a lot longer. You can do it. You could do 1/2 mv squared for both objects before the collision, and then do 1/2 mv squared for both objects after the collision. But those equations get even more complicated than these. Um, and with the V3 and V4 being both positive or both negative, depending which way they're moving after the collision, it's also a good reminder here that you want to pay very close attention to your positive and negative signs because it matters a lot whether V1 and V2 are positive and negative. The easiest way to get a wrong answer for these sorts of problems is to plug in positive or negative values when they're switched, right? Like if it's going to the right and right is positive, make sure you put it correctly, or left negative, etc. All right. Let's look at the last type of collision here. So that is called sometimes it's called completely inelastic or perfectly inelastic. Either of them is fine. We'll call it perfectly inelastic. What happens here is the objects stick together and move as one after the collision. Okay, let's draw what that looks like for a visual here. So object one comes in and hits object two after the collision. Both object one and object two are now stuck together. Leave a little more room for my objects there. Okay. And they both have one single velocity because they're now stuck together moving like they're a single object. So we don't have two separate velocities here, right? We don't have V3 and V4. We just have one, and we're just going to call it V3. Okay. We could also note with kinetic energy, because we've been talking about that the whole time, this is the most kinetic energy is lost. So of all three collision types, this is the one that loses the most kinetic energy. So going back to the first one, elastic, no kinetic energy is lost. Kinetic energy is conserved, the same amount before and after. Inelastic, the second one, some amount of kinetic energy gets lost into thermal, changed into thermal energy through the collision itself with heat and sound. In this perfectly inelastic, the largest amount of kinetic energy gets lost out of all three collision types. All right. Now, funny enough, we had the exact same equation for elastic and inelastic. Just the only thing we noted there was for elastic, V3 and V4 are opposite directions to each other as the objects move in opposite directions. Inelastic, we would see they're going in the same direction, so we'd get two positive V3 and V4, or both negative. All right, now for this one, the conservation of momentum equation looks just a little bit different. The start of it is actually going to look identical because before the collision, we still just have two separate objects moving at their own individual, unique velocities before they collide. So we'll put it the same first half of this equation, m1v1 plus m2v2. Now, after the collision, what we're going to do is we're going to do mass times velocity, but now we have one combined mass with the two objects like stuck together and treating them like they're one object that's just moving to the right. So the combined mass is m1 plus m2, and we take all of that mass times the velocity of that mass, v3. That's just a simplified or easier way to write the final momentum because they are combined together. So this conservation equation for perfectly inelastic collisions, again, the right side is the only thing that differs from the previous ones. But for all three conservation equations, it's not so much that you have to exactly memorize what elastic and inelastic look like. We just want to ask the question, what's the total momentum before the collision for object one and object two? And that doesn't change all the way through. It's just m1v1 plus m2v2. And then after the collision, what's the total momentum for both objects after they collide? And that could look like m1v3 plus m2v4, or in the case of perfectly inelastic, you combine the masses together because they're stuck together, times one velocity v3 after the collision. Just a single velocity for both objects. Okay, a couple just quick things to note is sometimes these will get a little more simple. There are a lot of masses and velocities running around, so there's a lot of numbers and values to consider here. Sometimes you would have a stationary object, like the second object isn't moving before they collide. That would entirely get rid of the m2v2 in the equation if you had that as the case. So, all right, real quick, I just want to wrap up with this same exact conservation, these conservation equations also work. They work just the same or just as well for, my K got really messed up there. Also work for what we're going to call generally explosions. Now, it sounds exciting, and sometimes we'll have an actual explosion. But really, that means you have two objects. See if I can draw a better flat line here. Two objects that are like together. Almost always they're going to be like stationary. You've got M1, M2. And this, I guess, it's not always the case. They could be moving together. So they could either, if they're moving together, they would have like one single velocity v1 before the collision. I should say before the explosion, because this one's not a collision. Here, your objects start together. So they're going to start off together. Your objects start together. Oops. Writing is getting all messed up here. And then they are pushed apart by some force. This is where the phrase explosion comes in. Sure, it could be an explosion. There could actually be something exploding that pushes these two apart from each other. It could be just a spring. There's going to be like a dog jumps off a skateboard. So the dog and the skateboard are the two objects and they're moving together, and then the dog jumps off. So this could just be like applied force. It doesn't really matter what force it is, because there could be a spring between them if there's a compressed spring and the spring pushes them apart, if they just explode away from each other, or applied force could be a possibility. So they start off together, and then after the explosion type scenario, then they're moving separately apart or away from each other afterwards. So the conservation equation has a lot of similarities with the starting and ending momentum. And going back to the very beginning, we said momentum is conserved in all collisions if there's no external impulse. So these forces we're talking about, explosion or spring force, if there's a spring between them and the spring pushes them apart, or there's a person on something and the person jumps off of whatever they're on, and they separate that way. All of those forces would be internal. So in all of this, there is no external impulse, which is really the key for conservation of momentum. If we can say that there is no external impulse at all, that's what allows us to say, hey, no forces are causing a change in momentum for this system, so momentum is conserved. Just like in Unit 3, we checked and said, are there any external forces doing work? If there's not, energy is conserved in a closed system with no external work. Same thing here. If there's no impulse from outside of the system, we get conservation of momentum. And it looks like this. Now, they start off together. So before this explosion, or whatever it is that pushes them apart, they start off combined. The objects together are either, they could be sitting there. It's possible that V1 is 0 and they're just not moving at all. And then a spring between them pushes them apart, or something explodes and pushes them apart. Whatever V1 is, it is 0 in some cases. The objects start together, either at rest together or moving with some velocity, like the dog in the skateboard example, where a dog is riding on a skateboard. It could be a person too, but there's a problem on one of your Schoology assignments, I think, that will end up being a dog on a skateboard. All right, so the combined mass together before the collision, or the explosion, I should say, means that the momentum is m1 plus m2 times v1. Afterwards, they're moving separately, but their momentum is still conserved. So the total momentum, this would be m1 v3 plus m2 v4. Now, however it helps you to write this, do whatever makes the most sense to you. Generally, they say v1 and v2 would be before the collision, v3 and v4 would be after the collision. In this case, the explosion or whatever pushes them apart. But if you get really weirded out by where's the v2, we're missing it in the middle, you could do v1, v2, and v3. That's not wrong. It's fine. Just make sure that however you set it up, that you remember this is the velocity before they push apart or explode or go their separate ways. This is the velocity. These two velocities are afterwards. So however you prefer to write that equation can work, But if you have the explosion type problem where they start off together and then end up separately, this would be what we'd use for conservation. And once again, it's not so important that you exactly memorize it. It's more important that you just look at the problem and say, all right, there's no external impulse here, so momentum would be conserved. And I'm going to look at the momentum before they push apart when they're together, and then I'm going to equal or equate that, set that equal to the momentum afterwards when they're moving their separate ways on their separate directions with v3 and v4 as their velocities. So yeah, it works just the same. All of these conservation of momentum equations for collisions and also for explosion type problems just say that the momentum at the beginning, before the collision or whatever happens, is the same as the momentum at the end. All right, we're going to call it there. We might see a few more details on conservation of momentum, things on collisions. But for this video, we're gonna wrap it up there. All right, so hopefully that helped get some foundation of how do we apply conservation of momentum in collisions, what are the types of collisions we can end up with, and how does momentum, or to a lesser degree, kinetic energy, apply to this? Because we're not going to do so much with kinetic energy. There might be a couple places where we'd actually use it, but mostly it's going to be looking at momentum for these. All right, thanks for watching, and we will see you all in class.